Good evening, everyone. My name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the eighth week of this particular course, and this is a 12-week long course. Instructor for this course is Professor Vinayak Kulkarni from Department of Mechanical Engineering, IIT Guwahati. And I also am affiliated to Department of Mechanical Engineering as a research scholar here. So today's theme is thrust augmentation, Ramjet examples, and introduction to Turbomachinery. So in total, three lectures are there. So before starting, I'll wait for another 5 minutes. Alright. After that, I'll start today's session. Thank you. So we can start today's session. So thrust augmentation, Ramjet examples, and introduction to the automation. So out of these three, so first lecture is on your Ramjet example. So not too much to discuss. In the previous weeks, one of the previous weeks lectures. Ramjet has been engine has been discussed. So three types of engines: turbofan, turbojet, and Ramjet engine. These three were discussed. So in today's session, we will discuss first augmentation, and then there is one lecture on introduction to turbomachinery. So there equations that govern the turbo machines. So mathematically that has been discussed. So in this discussion, it's very important that we have visualization of proper visualization of the velocities, the fluid velocity that the fluid that is passing through our turbo machine. So we divide it into components. So it's very important that we are able to visualize those components. Only then we'll be able to have a good hold on the velocity triangles related to such turbo machines. So that is a later part, but also on velocity triangles, we will not go too much into that. It's just introduction to that. So one lecture at a time, and then questions related to that lecture. So this way we will have our session. But in today's session, we have only one such lecture, that is lecture number 24. Already. Lecture 25 will discuss, but because in your assignment, we are not questioned on this, I believe. So we'll wait for questions to be framed on this lecture in the coming assignments. The first is from a previous week only. Then you have first augmentation and engine performance parameters for aircraft or aircrafts. Engine performance parameters, they have been introduced in most probably V2's content. And then some here the performance is related to your altitude, what will happen. That is also brief, but mostly the thrust augmentation. Thrust augmentation. So in thrust augmentation. So what is the need of thrust augmentation? So abrupt increase in thrust we need at times, and what are such scenarios? So this has been taught in lecture number 24. At takeoff, we need more thrust, right? So more than we require while the aircraft is cruising. Okay. Then when we are climbing, when the aircraft is climbing, right, it is trying to gain altitude. There also this is required. Okay. So there are two ways have been discussed. One is to increase the turbine inlet temperature turbine inlet temperature. Second is the second is to increase the mass flow rate of the fluid of or the air that is entering your engine, gas turbine engine. Then in thrust augmentation, then there are two more discussions are there. One is liquid injection. One is your after burning. We keep our discussion very brief because we have a very lengthy numerical to solve. Okay. These two are there. Then liquid injection. What is the purpose of liquid injection? Why do we do liquid injection? So liquid injection basically is done to increase the mass flow rate, right? So how it is done? So it is sprayed at your compressor inlet, right? And this liquid gets evaporated by heat from air. Okay. So air temperature at the compressor inlet decreases. So this somehow increases your mass flow rate. And what are the liquids used here? So two liquids have been mentioned. One is your methanol and ethanol. These two. Then is your afterburner. So what happens in your afterburner is that after your combustion has taken place in your combustion chamber. This is your combustion chamber. Here it has taken place, so it should go to nozzle. So what we do is we keep an afterburner here and here, and then we let it pass through nozzle. So what is the purpose of using afterburner? Again, we want to augment our thrust. And how are we increasing our thrust or augmenting our thrust? We are increasing the turbine inlet temperature. We are increasing the turbine inlet temperature. So before prayer, turbine is also turbine inlet. Yes. So what happens in afterburner is that whatever you're getting out of your combustion chamber, there some oxygen is still left. So we introduce again fuel in our afterburner, and again this with the help of this oxygen, the fuel is further burnt, and this augments your thrust. And it's Yes, diagram is something like this. So basically, after that, this is after this is knowledge flow with after burning, and this is after. Okay, so at present I'm discussing thrust augmentation. This much I have discussed. First step is liquid injection and then after burning. Then I have discussed the Phillips diagram for after burning. So this is the correct schematic. After the combustion chamber, you have your turbine expansion taking place at turbine. Then from there it goes to afterburner, and then again it goes to normal. And what are the advantages of afterburning? These are topics. Lecture number 24. First augmentation leads to increased stress. Afterburning, advantages of afterburning. Second is limitations of your afterburning. And the last topic is engine performance. So what are the advantages of afterburner? So it can increase your thrust by up to 40%. Okay, so that was a huge number. And what are the limitations? Limitation is that it will consume a large amount of fuel. So if we use it for large period of time, in that case, the fuel consumption will become high. So this is briefly about afterburner. Then in your engine performance topic, one important diagram related to thrust is this. So with altitude, what happens to your so this is sea level and your altitude is increasing downwards. So for same Mach number with increase in altitude, your thrust tends to decrease. Okay. So one takeaway from this topic is this. Then we will move on to questions. This is first question. So this is first question. You say that which of the following can assist in boosting the thrust of the aircraft engine? Four options are there. First is reducing the pressure ratio of the cycle, diminishing the mass flow rate and turbine inlet temperature. Turbine inlet temperature basically is the exit of your combustion cylinder. Raising the third is raising the compressor inlet temperature, enhancing the mass flow rate and turbine inlet temperature. So straightforward. Two methods we have discussed. One is your increasing mass flow rate and turbine inlet temperature. So D is the correct answer to this question. And next question. Out of four options, which one is correct? The question is on afterburners. It says that the afterburners in your turbojet engines are used. First option is to minimize the heat loss in combustion chambers. Second is to regulate pressure loss in the heating process. Third is to increase the maximum temperature of the cycle. Fourth is to improve the compressor inlet temperature. If you see the diagram, the purpose of afterburner basically is to increase the maximum temperature of the cycle. C option. Because we are burning extra fuel with the oxygen left. So your products from combustion chamber are coming out and passing through your expanding through your turbine and coming towards nozzle. So to increase the maximum temperature of the cycle after burner oil. So C is the correct option. So I was talking about question number 3, and it says that in case of a Rayleigh flow through a constant area duct with supersonic intake, the stagnation temperature along the length of duct. So what happens to the stagnation temperature if we have some duct and there is flow? With mag greater than 1. And Rayleigh flow basic means we are heat is being added here. For supersonic intake, the stagnation temperature of along the length of duct, what happens? So as the flow moves in this duct, so what happens to the stagnation temperature? Four options have been given. Your mag will decrease, okay, along the length, and your stagnation temperature, if this is 1, this is 2. So stagnation temperature at 3 will be higher than at 1. This is your Rayleigh flow. So stagnation temperature increases is the correct answer to this question. And if your m is less than 1, in that case this increases. In case your flow is subsonic, then your map will be. Then next question, question number 4. Again is on Rayleigh flow. It talks about CHO, thermal choking, or a constant cross-section passage having Rayleigh flow with thermal choking. The flow at exit of the passage should be. Subsonic, sonic, supersonic, hypersonic. So question itself talks about thermal choking. So at thermal choking, your flow is sonic. Okay, your Mach is 1. This is your question number 4 on Rayleigh flow. Rayleigh flow was introduced in your lecture number 24 to analyze the afterburners. So what will be the impact of this heat at the exit at the nozzle? This increased heat addition to an afterburner. So how this will affect your fluid flow? So for that, this Rayleigh flow was introduced. Then moving on to next set of questions. So this is a lengthy part or lengthy group of questions. Let's initiate this. So we will move slow here. So that we better understand this numerical. So paragraph says that the twin spool turbofan engine configuration consists of the following parameters. In this, the fan is driven by a low pressure turbine and the compressor is driven by your high pressure turbine. Separate cold and hot nozzles are used. So this is it. The twin spool turbofan engine has been given. Overall pressure ratio has been given 22.0, which is for your fan and compressor combined. Okay. Then fan pressure ratio is given as 1.56. Bypass ratio has been given as 4.5. What is bypass ratio? So this is turbofan engine. This is fan. This is core. The air that is being bypassed and not being used for combustion is your bypassed air. And this ratio is given here. We write it by B. B is given as 4.5. Okay. Then turbine inlet temperature has been given 1482 Kelvin. Okay. Polytropic efficiencies of fan, compressor, and turbine all are same at 0.87. Isentropic efficiency of each propelling nozzle is 0.92. Each propelling nozzle means one is for these sections. Okay. Cold part, one is for your core. For your core. Cold nozzle, hot nozzle. For each spool mechanical efficiency 0.99. So spool you understand, right? So the arrangement of your high pressure turbine with your compressor and your low pressure turbine with your fan. This is spool. Pressure loss in combustion is 1.45 bar. So this information is given. So I hope you remember in combustion we have pressure loss, and we would in this diagram we could show it this way. So this is your compression, this is your combustion, this way, and this pressure loss. Delta P. Then total air mass flow is 204 kg per second. Fuel to air ratio is this. Ambient pressure and temperature are 1 bar and 288 Kelvin. For air, CPG is given as 1.005 kilojoule per kg Kelvin. Gamma is given as 1.40. For gas, CP, so this is CPA here. So this is CPG. This is gamma for gas. This is gamma for air. This information is given to us. All right. Then based on this, we will solve questions now. But before that, we will write down, sorry, what is given to us. And also we will draw one schematic so that for each step we have numbering. Question number 5 to 11. What is given to us? Before given, we will draw schematic. This is your fan. After fan, you have compressor. After compressor, you have combustion chamber. After combustion chamber, you have high pressure turbine. After that, you have low pressure turbine. After that, you have hot nozzle. Here we have cold nozzle. Cold nozzle and hot nozzle are clear to us. I have just discussed it. So we'll give numbering here. So this is 1, 2, 5, 6, 7. This is 8. This can also be government. Okay, so pressure ratio is 22.0, total pressure ratio. For fan, it is 1.56. Bypass ratio is 4.5. Okay, inlet of your turbine temperature is given as 1482 Kelvin. Then polytropic efficiencies for your fan, for your compressor, and for your turbine is given as 0.87. Then for your nozzle, asymptotic efficiency is given as 0.92. This is given as this. So this is for transmission for spool. Okay, so spool arrangement, mechanical efficiency of each spool. So this is this 0.99. Then pressure loss because of combustion is 1.45 bar. Mass per unit of air is given as 204 kg per second. Also for air is 1.005 kilojoule per kg Kelvin, and gamma is 1.40. Okay, for gas, CPG is 1.148 kilojoule per kg Kelvin. Gamma is 1.3. So this is given to us. Then we will solve the questions. Fan outlet temperature is fan outlet temperature. You will calculate question number 5 solution for fan outlet temperature. What we do is outlet temperature. If you see this diagram is T02. T02. We need to find out. For this, we will use this relation. This is polytropic index, not to be confused with efficiency. This is polytropic index. Okay. For your compression process, or for your fan, or for your yes. for a compression cases. So, but this we need to find out. Okay. This N C minus 1 by NC we need to find out. And P naught 2 by P naught 1 is given to us. Okay. Fan, which is fan pressure ratio. For compression, now this is polytropic efficiency. Okay. This is polytropic efficiency. A minus gamma A. So if you place values in it, 0.87, 0.4 by 1.4, the result will come out to be 0.3284. If I have made some mistake, you can just let me know in the comment box. Okay. Then for expansion also we will calculate now only, which we will use in future. So this is polytropic index. Okay. Remember. Same is with this. This is polytropic index. So this is NTP gamma G minus 1 by gamma G, which is 0.87, gamma G 0.33, 1.33, gamma G is 1.33. So if you solve this, this will come out to be 0.2158. It will come out to be this. Now, for question number 5, we will come back to T02. T02 is T01. T01 is 288 given to us into pressure ratio 1.56. So I'm using placing values in this expression which we have written. So the exponent of this is we have already calculated. I have already calculated this above here. Okay. So this comes out to be 353.28 Kelvin. So question number 5 is done in that case. Three 33.28. So Then next question, let's see. Next question is thrust produced by cold nozzle. For thrust produced by cold nozzle, if you see the schematic, from 2 to 8 it is moving. Okay. So for thrust, what do we require? Question number 6. For cold stream thrust, call it FC. This will be mass flow rate of cold stream. Then velocity. Okay, C8. Call it C8. Mass flow rate will be one step to calculate. Then what we need? C8. So let's calculate mass flow rate first of all. This is mass flow rate of air into B by B plus 1. Okay. B by B plus 1, I hope this is understood. Because this is cold by hot is B basically. So cold by hot is B by 1. Okay. Implies C plus H is equal to B plus 1, which is total. So this basically is total mass flow rate, B plus 1. Out of that, B is the cold part. So putting values here, m dot A is 204, B is 4.5 divided by 5.5. So if you calculate this, this will come out to be 166.90 kg per second. Okay. Then now we need to calculate velocity. So C8, you can use this formula. So what we are doing here is we are basically converting the enthalpy that is there with the air by virtue of its change in temperature. The enthalpy change is being converted to its kinetic energy. Okay, this. Then this we need. So this is nozzle temperature drop. Okay. This is nozzle temperature drop. So this has formula. Efficiency of nozzle into P naught 2 1 minus 1 by P naught 2 by P naught 1. Gamma A minus 1 by gamma A. This. This basically is nozzle efficiency. This is nothing special, but just the definition of your nozzle efficiency. Then if we calculate this, the base values 0.92 into 333.28 into 1 minus 1 by 1.56. This is 0.4 divided by 1.4. This. Alright. So this is 36.58 Kelvin. Now this is clear where did this come from? Okay. If not, please write to me in the comment box. I just explain. I'll reach out to you. Okay. Then we can calculate our FC, which is cold stream thrust, mass flow rate of cold stream into. So this is 166.90. You are still left with calculating the C8. So implies C8 is equal to 2 into CPA is 1005 into this temperature difference, which is 36.58. And if I've calculated it correctly, this is 271.15 meter per second. So FC is 166.90 into 271.15. And if you calculate this, this will come out to be 45254.93 meters, which is roughly equal to 45255 meters. So this is your question number 6. The next question. So question number 7 asks for actual outlet temperature of high pressure turbine. So if you see high pressure turbine in your schematic, this is T05. So question asks for T05. Okay. Question asks for T05. This is question number 7. Question asks for outlet temperature of high pressure turbine, that is T05. Just have a look at the schematic again. So T05 is T04. So this basically is from, I will just write this first. Mechanical, this transmission is 2 to 3 is your compressor, 4 to 5 is your high pressure turbine. So this basically is your. So from here you can deduce T05. This. So T04 is given to us maximum cycle temperature 148 Kelvin minus 1005, efficiency is 0.99, CPG is 1148. Then P03, you have not calculated P03 yet, so just wait to put values. The P03 we can calculate from here. The T03 is, here we need T03. Okay. The T03 is T02 into T03 by T02. This is for compressor in polytropic process. Okay, NC minus 1 by NC we have calculated. So now here, but P03 by P02 we do not have at present. So we will just calculate it first of all. So P03 by P02 is P03 P01, P02 by P01. Okay, this is 22, this is 1.56. When we calculate this, this will come out to be 14.10. All right, this will come out to be 14.10. Now we can calculate. So P03 is 333.28 into 14.10 raised to power 0.3384. Okay. Now if you calculate this, this will come out to be 794.71 Kelvin. This will come out to be this. So now we have T03 and we can place T03 here. Here in our T05 expression. Hence, T05 is T04 1482 minus 1005 0.99 into 1148 into T03 is 794.71 minus T02 is 333.28. This T05, if you calculate 1073.96 Kelvin or roughly 1074 Kelvin. This is answer to question number 7. 1074. Okay. Then is next question. Okay. Before next question, we should take one short 5 minutes break. All right. After that, we'll continue with the session. Thank you. Okay, so we can continue with the session. So critical pressure issue for hot nozzle. This asks for this. Okay. Critical pressure ratio for hot nozzle. So question number 8. Solution. Critical pressure ratio is P naught 6 by PC is equal to 1 divided by okay. 1 divided by 1 minus 1 by efficiency of nozzle. This and then this. Okay. Now just place the values. One point three three divided by 0.33. So if you calculate this will come out to be 1.96 P naught 6 by PC. So this is critical pressure ratio for your nozzle. So we have this formula you can take from the intake and nozzle. This week's content, week number 6 will be right. So we are discussing question number 9, where we need to find out the hot stream velocity at the exit of the nozzle. So as you see the schematic, this is exit of the nozzle. So C7 we need to find out, and question number 9. So C7 can be calculated this way from the enthalpy only. T naught 6 minus T7 raised to power 1 by 2. Now we need T naught 6 and T7. So T7 we need to calculate also. T naught 6 we need to calculate. So these two we need to calculate. The first and calculate T naught 6. So this will come from this formula. So we'll write the formula first. So n mechanical equal to b plus 1 CPA T naught 2 minus T naught 1 into 1 CPG T naught 5 minus T naught 6 implies from here we can find out T naught 6. T naught 5 minus PA by n mechanical CPG T naught 2 minus T naught 1 this much. Now place the values T naught 5 we have calculated this B plus 1 is 5.5 CPA is 1005 12 3.19 into 1148 so T naught 2 is 343.2 minus 2 this. If you calculate this will be 853.77 Kelvin. T naught 6 we have calculated. Now we need to find out P7. P7 is from this formula. This is one. This is one. So P7 is T naught 6 minus internal nozzle P naught 6 1 minus P naught 1 by P naught 6 gamma g minus 1 by gamma g. So now place the values 853.77 minus 77 1 minus now 1 by P naught 6 we have not calculated yet. Other things we have 1.33. So for P naught 6 for P naught 6 P naught 6 is equal to P naught 5 P naught 6 by P naught 5. Okay, this is for your turbine expansion. P naught 5 is P naught 4 into P naught 5 by P naught 4 in the n minus 1 and P naught 4 is P naught 3 minus delta PB which is 22 minus 1.45 which is 20.55 bar. Okay. So P naught 5 becomes 20.55 into 1074 divided by 1482. So these things we had, and this also we had calculated in the starting. Question number 5 we have calculated this. If you calculate this, this will come out to be 4.62 bar. Okay. I hope this is clear. Then P naught 5 we have, then P naught 6 we can calculate in that case. Okay. So P naught 6 is P naught 5, which is 4.62 into T naught 6 we have just calculated 853.77 divided by 1074, which is T naught 5 to power 1 by 0.2158. So this also we have calculated in question number 5. So if you calculate this, this will come out to 1.59 bar. Right? P naught 6 is 1.59 bar. Now P naught 6 we have, okay, and we can place this here. P naught 6 can be placed here. This value is 1.59. 1.59. Now if you calculate this T7, implies T7 if you calculate by placing this 1.59, this will come out to be 768.39 Kelvin. So T7 will come out to be this much. Okay. In that case, hence T7 can be calculated as 2 into CPG T06 minus T7, which is 2 into 1148 into 853.77 minus 768.39. So if you calculate this, this will come out to be 442.75 meter per second. So this is your hot stream velocity. Okay. The next question asks for after this 442.75, two more questions are there. But I believe I'll skip those two questions because we are short of time. We're left with about 15 minutes, so I'll just discuss the two questions are left. If some other time I have time, just spare time, we can discuss these. So lecture number 25. So introduction to turbomachinery. So Euler turbo machine equation, torque and power. These two main expressions. So Euler turbo machinery equation. So here first momentum equation has been discussed, right? Which basically is time derivative of your velocity vector and then your fluid element mass. Okay. So this is for your some fluid element linked to your turbo machine. Right? And if you take the moment of this, if you take moment of the above equation, so this will come out to be this. So this has been covered in detail in your lecture number 25. Right? And then later this torque from here for some turbo machine we find torque. So they are components of your fluid that is entering in your turbo machine. So this is the total velocity, okay, of the fluid. It will have three components. One will be your radial component, one will be your axial component, and then one will be your tangential component. So CR1 is radial, this is axial, this is. It is very important to visualize these directions, only then you will be able to make sense out of the velocity triangles. So if this is your shaft, right? This is your shaft, and it is moving in this direction. So this direction is your axial direction. Then at this point, if you see, if this is your rod, okay, this is your rod. In that case, this is this way. This is your tangent, okay, tangential. This is your axial direction. This is your tangential direction. This is your radial. radial direction. Okay, towards your axis, perpendicular to your axis, okay? And then parallel to your axis is this axial direction. Tangential is with respect to your circumference of the shaft. Right? It will be tangential to that. Something like this. This will be, if you can visualize, this is radial, this is axial. So I was discussing Euler turbomachinery equation, and for that I have introduced the momentum equation, and then moment of this momentum has been taken, right? And then we are trying to understand the velocity directions of different components of the velocity. Then the torque related to shaft, there is expression for that. This is this like this. So this basically is your this Euler turbomachinery equation, and then this is mass flow rate of fluid. This is radial direction of fluid. So if we are taking 2 points, between 2 points, we want to calculate the torque related to this fluid, right? Then at this point and this point, this is one and this is two. So add two, what will be the radial position? Okay. At one, what will be the radial position? And at these two positions, what will be the radial direction? If this is the shaft, if this is the shaft, then something like this, tangential velocity CW2 and CW1. Okay. Then power from here you can calculate. Power you can power is our shaft into your angular velocity. So this will become power will become m dot r2 omega c omega 2 minus r1 plus omega. So this will become due to c omega 2 minus E1 C omega will become this. So this is it. Right. Then one brief about just one quick discussion on this. Alright. But this is from your lecture only. This is blade and this is the movement of a blade. This is your inlet. So it's U2, V2, this is U2, this is U1, this is U1. So C is the absolute velocity, V is your U is your this rotor or shaft, and V is your relative velocity. So I hope you can imagine, you are able to imagine this. So there are two velocities, first of all, involved. First is you have some shaft and you have some blades here. Okay, you have some turbine. Now some fluid is entering in this turbine, right? So first of all, you have velocity of your fluid, but also when this fluid is entering, this turbine will have some rotational movement, right? About its axis, so it is moving. So then it will have this U, all right? And then these two velocities will interact. So this will have one resultant relative velocity. Okay, so that is, I will set V. Okay. Then here the components of velocity have been given. So if you see this component only, this between the dots, this component is the tangential component. And this, sorry. So this is related to your fluid velocity, okay? And this component is, yeah, radial. So please note, here we are taking two components only, right? As if there is no movement in the axial direction. So radial and your tangential. So you can also imagine Pelton turbine, you can imagine. So only in one this R and this tangential direction. Two directions only are involved. No axial direction. Right? If this is your shaft and blades are like this. Okay. If like blades are like this, so fluid will come in this direction. There will be no movement in this direction. So this has been discussed in your lecture. So this is something like that. Right? The same is for here between these two dots. This is your C tangential and this is your radial. Okay, I hope you are able to imagine. Then if you want to calculate the work involved, so this expression has been given here is so it can be given based on the three velocities that we have discussed. Minus half of v1 square v2 square. So this can be also used. All right. Other than this, if you have to, for let's say if we have some compressor, okay, so this is turbine work, right, which can be equated to which this way this can be. If you see this equation, like, so it can be equated this way. All right. Then if you have to, if you give example of compressor, enthalpy and power. If you have to relate enthalpy and power for compressor, if you take example of compressor, it will be this. C omega 2 minus omega. This is for a compressor. Okay. Then also the pressure change across the turbo machine. What is their relation with the velocities? So for your compressor, the pressure change can be related to these two velocities. One is your the shaft moving, and then other one is your relative velocity. So this is a discussion that has been done in your lecture 25, and we have come to the end of this session. In that case, I'll conclude this session. So there were three lectures. First lecture was Ramjet, examples of Ramjet engines, right? So that we did not discuss. Then second, because it has mostly numericals. So second was your thrust augmentation. The discussion on thrust augmentation. So two ways are there in which you can augment thrust. One is by increasing mass flow, and another is by increasing the inlet temperature of your turbine. Also, so we saw liquid injection, how liquid injection in your compressor, right? At the inlet of compressor, it increases the mass flow rate. Then we saw afterburner, right? How it helps in augmenting thrust. Then we saw questions from here, right? Very basic questions. And, then we saw numericals based on your turbofan, right? And polytropic efficiency, the concept of polytropic efficiency was included in this numerical. And we saw how to use this for your compressor and for your turbine, polytropic efficiencies. After that, we discussed lecture number 25, which is basically introduction to your turbo machines. So there are levels in which we are being introduced to turbo machines. So initially, the tools content, I believe we discussed, we were introduced to turbo machines, and then now we are moving a step ahead. So we have reached to the velocity triangles. Right? It's very important that we are able to visualize the velocities involved in the turbo machines related to fluids. So that is it about this week's content and assignment questions. Questions related to this week's content. And thank you in that case for watching this session. And next session again will be on coming Tuesday from 6 to 8 p.m. You all are welcome to join this session. Thanks a lot.